My name is Nicolás Lorente, and I'm working in the Centro de Física Materiales in San Sebastián. I would like to talk about the principle of electron spin resonance using a scanning tunneling microscope. Usual electron spin resonance is based on inducing periodic transitions between two states. Now, in electron spin resonance, the field is an external magnetic field. The two-level system is a spin system, so they naturally couple together, and it is possible to induce dynamics between the two states using this external magnetic field that is changing in time. When you're using an STM, the electric field is the one that is modulated in time. The problem is, how do you couple an oscillating electric field with a spin? Before understanding how these two quantities couple, let's study a little bit the two-level system. Let's take two states, 0 and 1. This defines a simple Hamiltonian, which is a 2x2 matrix. The first element will be the on-site energy for the first state, 0. The second element will be the energy of the first or number 1 state. And the interaction between the two states is given by V. We can solve this Schrödinger equation. For that, we need to give some initial condition. We take the wave function at time equals 0 equal to the wave function of the 0 state. Then we can solve the Schrödinger equation, and it gets pretty involved, but it's just a linear combination of the two possible states that we have in our system, phi naught and phi 1. Let us look into the dynamic part of this wave function, given by the phases written here. As you can see, the phases, this E minus and E plus, actually depend on different quantities that are related to the different energies of our two-level system. C1 and C2 also depend on quantities, which is the difference between the two levels and the interaction, but they don't give us information on the actual dynamics. Let's only focus on the dynamics. The first thing that comes to mind is the Larmor or precession frequency, this omega naught, that is just the difference between the two levels. And it's going to tell us when we are on resonance for a given system. The probability to find one of the levels populated is given just by the weight of the function of that level into the full system function at a given time and modulus squared. So that is exactly the element 111 of the density matrix, or the population of that level at a given time t. We can solve it for this case, and it turns out to be just an oscillatory function. You see it's a sine square, so it means that the frequency will be double this number here of this oscillatory function. The population of the 0 state will be just 1 minus P1, because the sum of the two population has to be 1. This defines oscillations that are given by the frequency omega equal to twice the square root of the difference between the levels and the interaction between the levels. This is called the Rabi frequency. When we drive the system, our interaction is now modulated in time at a given frequency omega. We can do the same calculation as before, and we find that we have to change the Rabi frequency into a little bit more complex expression, where now the driving frequency appears explicitly. When we are in resonance, we find that we can cancel this term here, and the Rabi frequency becomes twice the interaction between the two levels. So we can change our Hamiltonian of the two-level system by a simplified Hamiltonian, where the non-diagonal term clearly shows the dependence with the Rabi frequency. So this is very interesting, because immediately it is telling us if a Hamiltonian can give us an ESR signal, because the Rabi frequency will tell us the rate of transfer between the two states 0 and 1 and whether we can have resonances. A second important ingredient to have an electron spin resonant active system is to have a low decoherence time. This is because decoherence causes jumps, random jumps between the phase in the phase between the two states. If you have a random jump, then you don't have oscillations, and then you don't have any more two-level system dynamics. The electron spin resonance mechanism is based on an applied electric field that will induce an alternating current. But this is bad for ESR because it increases the decoherence. What we need to see is how this time-dependent applied bias leads to Rabi oscillations. And the problem is that it needs to couple the two magnetic states. To have coupling with the magnetic states, what we need is a magnetic interaction between the tip and the magnetic atom. And what I would like to show quickly here is that this is equivalent to an oscillating magnetic field. Take, for example, an exchange interaction between the tip and the atom. So an exchange interaction is given by the spin of the tip dot product spin of the atom, weighed by some interaction J. And if we assume that this is basically a classical spin, then we can just take the expected value. And this full object here is just a vector. So it behaves the same as a magnetic field. And we can have the same sort of interaction as a Zeeman interaction between an external magnetic field and the spin. But still, we have not solved the problem of how this magnetic field is changing with time when we apply an AC bias. For that, most of the workers in this field agree that there must be the motion of the atom. We need a strong piezoelectric response if we want the atom to move in the applied electric field. There are also other possibilities to make a electric field producing a magnetic field that changes in time, and that is changing the tunneling probability in time. Electric fields are good for that because you are changing the probability that the electron hops between the tip and the sample. This is the scenario that we explore in this article cited here. Thank you very much for your attention.